Good afternoon. As you know, today this is the third lecture on simulation with one interlude of data mining. And today it's design, modeling and simulation. I must say, this is probably the lecture that was hardest to get to because just this morning, actually very early in the morning, I was still in Beijing. This is an example from Beijing from yesterday. And I think if we take simulation in architecture serious, we can have these type of images and decisions before we actually build these things, and that might be very beneficial. This is not a simulation, this is reality or a picture taken just yesterday. This is also reality. This is the workshop and the conference that was done for us, for ETH, as you can see here, Swiss Federal Institute of Technology, on cognitive science, medical science, healthcare and ICT. And that, of course, is also related to our field of simulation. It's not information architecture, but it's information science combined with medicine. And this is one of the most unreal images I took last night, 2 of them. I think it's the only time I've ever been there in the biggest airport of the world, totally alone in this entire huge airport, going from one end to the other, and nobody else was there. So this is looking down one way, unfortunately a bit shaky, looking down the other way. There's one tiny, I don't even know if it's a person or just a statue there in the back, but that was quite eerie. Of course, the entire airport only lit and heated, in this case for one person, seems not to make sense. These are things also you can take care of with simulation. Maybe it doesn't make sense to have this whole airport open. Maybe then the planes should go from another place. Also, one very actual image is from here. I don't know if you can see it, but this, I come a bit closer. Can you see it? Well, not very good. It's very fuzzy. Anyway, this is a simulation without time of the new Value Lab Asia. So the equivalent, the mirror of where you are in now. And we're using this type of visualization, modeling to convince the people, for example, not to put in a hung ceiling and things like this so that the space remains open, as it is in your case. Okay, let's go to today's lecture, the content. We want to revisit briefly urban data mining and give you examples that I couldn't show last time because of time reasons. But there are 2 very distinct examples. One is a historic example and one is a new example. Then we look at design and modeling. These are 2 distinct activities, of course. That's leading us to modeling and simulation, and then specifically simulation and urban design, and some conclusions. As we go back to the data mining issue, this is also very new. This is from the Thursday, 3rd of November, last week, where we see that whole cities are emerging as so-called digital cities. In Australia is very active in this area, because Australia, by the nature of its geography, is very, very stretched apart. And in Australia, digital communication and digital exchange was a big issue. And now whole cities are taking this approach. So it's the e-government thrust into the future with its support. Brisbane, Australia, is also involved in these efforts. So this is an example from Brisbane, but there are many other Australian cities which are diving into this efforts. So what do you need for that? Of course you need data. And how do you get to these data? By collecting them and then through data mining that we explored last time. When we look at applying this data for cities and for running cities, managing cities and so on, I want to give you an example from the past. This is now 5 years ago. That is like a very, very long time in digital development. And this is example from our colleagues at MIT when they did a study on Rome, which was very interesting, as you will see in the next slides. So, for example, they were looking at the mobile devices people were using at this time, visualizing the intensity of mobile phone calls at the present moment and comparing it to yesterday's data. They looked at different aspects, and this is really data mining for many, many people. You could also call it kind of crowdsourcing, as you saw from Dongyeon Shin last time, but this one here is just taking specific data and one bit of data from many, many people, not a stream of data from few people. So the example one was pulse. What are the patterns of use in this city? And this is the city of Rome. You recognize it, the river, the Tiber here with the island. Maybe you can recognize here the central train station, and you can see where people are at certain times just by looking at the mobile phone use in these areas. So this is a very busy area, this one here. And then during the day and during the evening, the night, and during the day, you can see here very clear different patterns. So you see how people are moving from one to the other place during the day. Another example from the same study is the connectivity. Is public transportation where the people are? So you look at different places, look at the movement of buses, and look if that overlaps with the position where the pedestrians are. So let's have a look at this. This is actually a little bit animated. You might recognize the area here. This is the, who knows that place? Say it, you connoisseurs of Rome. Anyone from Italy there? This one here? Can see it? Or can you see the cursor at all?
It's not Roma Termini.
Anyway. Yeah, of course. Great. Yes, this is Roma Termini. And there's a lot of people and also a lot of buses. Here the buses seem to be stuck. In other places we see some traffic, but here in other places where you have many people, there seems to be not very much traffic buses. So this overlap is not so great. We will see much more of this in our data from Singapore and from Zurich, where you can see where we have much better data situation now, and therefore also a better data mining situation. The third example is the flow. Where's the traffic flowing? And this is also very nice because it's such a old example. Today, of course, you can depict that much more interestingly, graphically, and the MIT people have refined this method in the meantime tremendously, but here we still see the original representation. So in this next example, red indicates areas where traffic is moving slowly, green where it's moving quickly, and the arrows show in which direction mainly it is moving. So here we have a look at this, and you can see right away down this big street here, you have these arrows, and red is slow and green is fast. It's not very intuitive at this moment, I would say, and this was one of the reasons why they improved the visualization of this project real-time tremendously over time. Today, this is, as I said, history, but it's good for you to see where it came from. And finally, this is something that brings us more into three-dimensional visualization. Where are tourists congregating? Where are the concentrations of foreigners, highlighting the locations where tourists are speaking on mobile phones? And there you see, again, the train station here, and then you see areas next to the train station, and of course all the area around the Colosseum here, and the old part of the Roman city, where most of the tourists are, and talking and SMSing probably a lot. And the final one is where now we take into account also time as a continuum. We look at gatherings. What does the city look like during special events? Because we expect, of course, the city to have more people in certain areas, but we do not know how many more people. So there were two events taken. One was the World Cup final match between Italy and France on July 9, 2006, and the celebrations at the arrival in Rome of the winning Italy national team on July 10th. This is one. And then Madonna's concert in Rome on August 6, 2006. So you can imagine many people arriving at this. But now this gives you a very good spatio-temporal representation of these two events with data mining techniques. So look at this. It's like a net spread over the city, and the net is now performing. At the top you can see time running, and here you can see where it gets dark and the net is lifted up. That's where the activities are. And then you see here again at the front, Roma Termini, where all the people are arriving, a huge peak of activity coming in. And then in the afternoon, the same thing, or the next day the same thing, when the team from Italy came back to Rome. So this is a very good example of a spatio-temporal representation. And a city, although it's a static structure, has to take care of this very, very strongly fluctuating number of people and movements. So this was probably one of the first times that you could really visualize these things, based on data and data mining that you got directly from the people themselves. Okay, I think this you have seen, you got the idea. But you can do also other things with it, and that is kind of scary. Does somebody know this particular example? Whoops, now it wanted to kick me out again. Has one of you read this particular article recently in a German newspaper? No? Okay, so it shows again, this is a further development, it shows again what telephone companies basically have stored in terms of data on the location of the people who call and what calls they make. And one person or several persons, they wanted these data from the telephone company. First they didn't get them, but they then were able to get it from the telephone company, and they made it public on the web in order to show how much the so-called storage data approach is collecting in terms of data from you, from any one of us using this technology. And then they looked at this, and here hopefully it works. We see the application. Can you see that? Yes? Can you see that? Okay. So this is a map of Berlin, and this down here is the time. This is every day, September, October, November, December, January, and so on. What this particular person, Malte Spitz, also did was to make available his calendar, his public calendar that he as a member of parliament has, and then he linked, or he allowed the link of this calendar to the location data received from the phone companies. And this is now quite amazing, because with this, now we can increase the speed. You could see exactly where he was traveling by different phone calls he made. So he went from Berlin to, I can read it here, what is it, Ettlingen. There he stayed for a while, and you can see that little pointer going down here, jumping to the next morning. So probably he was sleeping now in this city. On the right side you can see the time running here. On the right side you can see what his official calendar was. So he goes with the train, continues to Munich, and you see all these little slots where he made phone calls, or where his phone was captured by one of the, or registered by one of the antennas of the mobile phone companies. And it's listed how many phone calls he had during these days, how many news he got during these days, how long he was online on the internet, more than 20 hours. Then the next day, on the 2nd December, he's back in Berlin. You can see it's in the morning, he is sleeping probably. Now let's speed up the process a bit more and also look at the map of Germany in this case, of Berlin. So you can see now where he is traveling in Berlin, always caught by these mobile phone location devices. If you look at it at a larger scale, here we can see he's in Berlin. Now he's sleeping again. Speed it up. He's not moving very much. He's making phone calls, as you can see by the little flickers here. And now he's moving in Berlin. You can zoom in and look where in Berlin he's moving around. So he claims that the telephone companies and other ones can have this data on you and each one of you, and that this is quite technologically, of course, very, very impressive. But if you think of the implications, needs to be discussed really deeply. And you can see following this during the whole day or year, actually, and see every single train travel he takes and where he goes in the different places in Germany. And if you link that to his official data, you can see an incredible amount of data that is there on each one of us. And using data mining, then you can use this to follow a single person, as an example. Okay, I think you can think about this yourself, what that means. This is tracking people, basically, possible today. For buildings and the behavior of buildings and tracking of energy flows in buildings, for example, or other flows of materials in buildings, I think this would be more our field, and I think it would be much more interesting. However, unfortunately, the software that we have for these fields is not as powerful as these mobile phone devices are. And this is why, for example, Dong Yongxing is using mobile phones to program his applications. Okay, short interruption. Questions to this? What does it have to do with architecture? What does it have to do with the city?
You could set the capacity of the streets or infrastructure. If you follow everybody who has a mobile phone, you can tell how many people flow where, and then you can decide the sizes of spaces.
Right, so this would be a very good application to see the capacity. If you had it from all people, of course, then you would have to guarantee that everybody has these phones, uses these phones. But I think with statistical analysis and statistical measures, you could calculate that for the whole city. Absolutely. Also, where people get together, if you look at this example from Rome before, and you see that at this Roma Termini, you have this incredible peaks of thousands and thousands of people coming at the same time. This is, of course, indispensable for planning of events and planning of buses and all of these things. Yes, I think so. There's a very close connection to that already. This also goes not only to the city, traveling between the city on the ground, because as you just saw from the last movement on the screen, it also catches the movement between cities by plane. This is then just assuming that the person was flying from city to city, so that means suddenly popping up on another city would mean that the person has flown there or was out of sight for a while. Do you still see the signal, or is it lost?
No, we lost the signal. Okay.
It's back now. Okay, good. All right, good. So these are some applications. Let's go back now to our topic today. The second point, design and modeling. Before we can do simulation And you remember simulation being the important link between theory and experiment in science, and between theory and design in architecture. We have to do some modeling. So in order to do a simulation, we need a model. And in this model, geometry sometimes is very important, but also time is very important. How do things change over time? How do they change in terms of space? So time and space are two important things that make a model. Here I show you some ancient examples again, how we tried to attack this topic in our previous works. This is now work from the chair, or from the predecessor of this chair, already 20 years ago, but this is, has not changed since then, because here we have different methods which we try to build models, information models of architecture. So one model, for example, is the stepwise refinement of a floor plan, as you can see here on the top, by Durand, of course. You divide it, you subdivide it again, introduce elements, and you do that by shape abstraction. You know that this axis is really an important abstraction in architecture. It doesn't mean that you have a line on the floor or a wall in this building, but it just means it's an abstract ordering principle. You use that in order then to design this building. So using the abstraction of lines, you come to a model. Or here in this one, again, you start with the cross shape of the abstracted center lines, then you place shapes around it, you strengthen the importance of certain shapes, you take away certain walls, and you end up with the floor plan of this particular building. In the old days of postmodernism, some of you might remember this building that was from the 80s already, a theater, a floating theater. Everything was symmetrical and quite easy to model. The abstractions at this time were also quite easy to do. So the geometry could be abstracted simply. And then also, for example, the acoustic abstraction, which we see here, could also be captured easily in a model because everything was symmetric. Another type of abstraction is the graph, showing how parts of a building or spaces in the building are related to each other. This is a very important abstraction. Or the other one is these bubble diagrams, or the functional diagram of a building. These things you have learned certainly in architectural education, no matter where you did that in this world. As a matter of fact, this way of designing is still used in China. My colleague Christophe Giraud, and you know Christophe Giraud, who is here right now on his time in Singapore, was in Nanjing the last week, together with other members of the faculty, with Sascha Menz and also with the Ludger Hofestadt, and they reported back to me that many years ago, 20, 30 years ago, students like you came from China to ETH, were educated there, went back to China to Nanjing, and introduced the methods, the abstraction methods in China, in Nanjing at this time. And they said they can still see very, very strong links between the education at this time under Professor Kramel at ETH and today's Nanjing's education. In some cases, really to the very same examples. So these things have a long history. Another abstraction is if you go into so-called grammars, very simple grammars like shape grammars or fractals as simplified shape grammars. When we have a lecture from Jan Halach towards the end of the semester, you will see much more about grammars and how you can use them. All the people who use City Engine and this course know these are based on grammars. So simplified grammars are fractals, and with fractals you can recreate all kinds of shapes. So the rule, the shape rule, is an abstraction of the generation of the tree or the plant or the floor plan or this Hilbert curve. And then you can use these abstractions, move them into a model, and then use these models to create simulations. Simulations, for example, of light over time, how it changes over time, or a simulation of heat transfer that you can see here how the heat is going from the inside to the outside of a building, or here in Singapore it would be the other way around, from the outside to the inside. So these are some examples of design and modeling, how they are related. Now we move to modeling and simulation, how they are related. First I start with something which is not simulation. Can you imagine what this is? Who has ever seen something like that? Now this is true, because you could not have possibly seen something like that, because that is so brand new. This is the inauguration of our Being There laboratory between Singapore and ETH and North Carolina State University, and it is the newest way to simulate telepresence in another place. So this is a robot. It's not a robot, it's just a puppet dressed in the NTU's, Nanyang Technology University's dress, sitting in Singapore. And the counterpart of this person could sit anywhere. It could be in a value lab where you are, or somewhere else in the world. But it is not a simulation, because it's a simple projection of something that you see in another place. In this case, could be anywhere. And this projection of another person, which is captured by his real feature, this is the face of this other person, is projected from the inside to the face, to this plastic face, this plastic hat actually, so that it looks like a real person. And not only does it look like a real person, but this hat here, this whole face, can move to the right and the left. So if you talk to this thing and stand on the side where this gentleman is standing, he will turn the head to your side and look at you, and his facial expression will change because it's mapped directly from where this other person is speaking to you. So imagine this was like me. I'm sitting here, but now I'm standing in front of you as a puppet, if you want, or as a styrofoam thing with a three-dimensional head, and what I'm saying and how I'm moving is projected to you directly. But this is not simulation, this is just projection. So this is the close-up view from this, and you can see it's not very, very good. But if you see the real person who's behind that, who was sitting next to it, so this is the real guy. I cannot stop it. I have to stop it. Sorry. Too fast. Anyway, this person is sitting in another place and looking through cameras at the space where the puppet is sitting. And therefore he has these different screens. If somebody steps into his view and talks to that puppet, he can see that person. He turns his head to this person who talks to him from remote. These little cameras up here capture where he's moving his head and then move the head accordingly on the other side. So you see, it's quite a complicated contraption, but this will be a setup that you will see many more times. This is a research project, but I think it will have many applications in the future. But again, it's not simulation. It is data transmission, and it looks as if you were. This it has in common with simulation, but it is not simulation. Okay, now I said so much what is not simulation. Let's get to some points how we could use architecture in simulation in architecture. This is a bit more dry, but I think relates much more to architecture and why we should use simulation tools to predict that and how buildings will work, to achieve low energy building life cycles, to reduce emissions, to optimize processes, and to improve life and work qualities for users. So if we could simulate all the things that you see here, it would be much easier to build better buildings. And these curves just show how important it is to do the simulation at the beginning. So you do the simulation at the beginning in this phase, in the design phase. The costs for changes are very small, and the possibilities for changes are very, very high. So this is where you can use simulation, and later it changes again. There's another chance where the two come closer together, and this is in the modernization phase, like in the building where you are now. That phase will happen in about 30 years, but not very early. The buildings next to you, around you, behind you will be modernized much quicker, and there again the possibility for change are high. That's when you should use simulation for reducing costs. How much does the simulation cost these days? A thermal simulation. Name me 2 programs that you know for thermal simulation. Do you know any? Today you all look like frozen. You are very quiet, and it is very like in a winter scene with all this brightness. Okay, who has used this thermal simulation programs? I'm sure you must have used it in Professor Leipengut's course, for example, with Arno Schlüter, or even with Jan Halacz. Any idea? How about Ecotect? Any heard of it?
Yeah, I just
Yes, no?
remember the name.
Okay. How about DOE2? No? How about Energy Plus? No? Oh my God. So that means I think I think there's some homework to be done. So please try to look that up on the web or in the courses that you had. Programs for thermal simulation, programs for CFD, computational fluid dynamics simulation, airflow simulation, for thermal FEM simulation, for electrical and daylight simulation. These are programs that are actually used in practice today. I thought, wrongly so, that you know all these programs, but if you don't, please look up some of them to get an understanding what they can do. I'll show you some examples later, but this is important. We just put down the price range, how much it could cost. This is not only taught at the ETH, but also at the Fachhochschulen, even more at Fachhochschulen maybe. And you can see the price range from 1,000 to 50,000 Swiss francs, depending on the size of a building. But if you get into real big-time simulation, for example, for a nuclear power plant, which has to be done very, very carefully today, for example, the new nuclear power plants that are planned in Finland, the simulations alone for these power plants cost in the range of 500 million Swiss francs or dollars. So it's a huge amount of money, which is more than 10% of the total cost of the building. That means if you did a wonderful simulation for a building that costs $1 million for a normal house, and you did a perfect simulation that would cover all the possible aspects that we know about today that you can simulate, and you would invest 100,000 Swiss francs in the simulation, 10% of the house cost, that might lead to a much better house. But this is, of course, something nobody wants to invest at the beginning. Here are some types of simulation. The thermal space simulation, here you have the time axis, here you have the temperature axis. The CFD simulation, the airflow simulation, the FEM, the finite element analysis simulation here of a joint, and the electrical daylight simulation that you can put on a schedule or simulate schedules in buildings that you don't want to have dark overnight, are just a few examples. Let's zoom in. Thermal room simulation, where you simulate comfort, building technology, and consider dynamic of external demands, of internal demands, and operation of housing technology. So these are different simulation types in rooms. Here the airflow simulation that I showed before. If you don't know what that is, really also go to Jan Halacz, and I make sure that when he talks in his lecture that he gives you a few examples of that. And these finite element analysis for thermal purposes, for thermal transmission simulation, thermal bridges, thermal storage properties, surface temperatures, and fire protection. What we have today is different tools that are dealt with by experts, and that might be a reason why you don't know these tools. If you don't happen to have in your previous education an expert on airflow or humidity simulation or acoustics, then it might be that you never hear about it. If these simulations were more integrated into actual design processes, then it would be much easier for you. And this is what we want, to integrate them in the design process. So defining the requirements, then doing simulation evaluation, redefining the geometry, redesigning the whole thing, and having a circular process here. Only when that is satisfactory, go into construction, building, design, life cycle. Where have we used simulation in the past? You could say this one here, the Neue Monte Rosa Hütte, New Monte Rosa hut in Switzerland, is sitting very close to a glacier. You could simulate, or you could have simulated this glacier, because you can see the line here. This was the line of the glacier hundreds or thousands of years ago. The glacier is now very much down here. So if you had a thermal model and a behavior model of this glacier, and you could have predicted that in the year 2010 and 11, today that is, the glacier would have melted from here to here, that would have been a simulation of the situation. And we, of course, now today we have climate models, and we're simulating what will happen to this glacier. Maybe it will disappear altogether, or if a new ice age is coming, that then it might grow and grow and grow again. But so you can see, and you can also test, if you go back in history. Remember 2-3 lectures ago we said that we can not only forecasting but backcasting, and take a situation from the past, try to predict the future, simulate the future, and then actually check if it's true. By the distance here, high time or high level of the glacier and low level of the glacier. This is the building, this is the glacier now in winter when it's all snowed over, and this here is a visualization of the building. It's not quite a simulation, as you see a visualization of the building, and then the real building here. So this is not a simulation anymore. Simulation of light over time in this building here from Foster & Partner in London, the City Hall, and you can see the light and also the energy and the heat losses that you have for this building. Simulation of geometry and changes of geometry. You could move this this object here. You could twist and tweak it, of course. Simulating structure. The bird's nest in Beijing that I was just driving by. Actually, today it looks so alone again, like in this visualization, because the Olympics are over. Many of the functions that were around it have disappeared, and it has a different use now. So what is stayed is only the geometry. Its use has already changed from the Olympics, but in this case, a structural program and geometric modeling and simulation were used to determine the final shape of this building and the shape of this interlocking bird's nest structural elements. Or here, airflows in buildings that you can slide a plane through these buildings, and here simulate, for example, the spread of fire in a building, or the escape routes and the drafting of the escape routes of people. All of these things can be simulated today. And more, and more, and more. Here, this, for example, dust, smoke, pollution, fire, very, very important, so that you see under certain conditions where the fire will spread, also that people run in the right direction and not in the wrong one. So all these things you can simulate today by combining the simulation with, for example, the steering of people in an automated system, that it points you in the right direction to escape the building, not into the wrong one, this can be deciding over life and death. And of course also simulating acoustics. This is fascinating, that you can predict basically the sound quality in any time of these wonderful new acoustic elements anywhere in the world by simulating the acoustics in very, very complex shapes here. Disney Hall in this case, or also in this case in Hamburg by our colleagues Herzog and Demeron, which also was heavily simulated in terms of music and acoustics. Simulating crowds of people, how they move. This is bringing us into the area of agents moving, but this is very, very interesting also for escape routes and dealing with people in these huge cities now where you have tens of millions of people having to be moved. You saw before in Rome all these people congregating around the train station. Here you can simulate this and then check it if it happens in reality and keep adjusting simulation and reality through the models that you use for the simulation. You can also simulate buildings. This is the building that we are in. You can simulate it. If its simulation is good, you give it a label, in this case the Minergie Eco label, and you can simulate the CO2 emission of this building, which was done, minimize energy consumption, simulate the flow of air and flow of heat into and out of this building, minimizing the energy demand of this building, digitizing it into different thermal zones, in this case 160 zones, and then making the geometry more acceptable or changing the geometry so it's optimized for this particular airflow and also light coming in and heat coming in, and then having the result. Then of course you have to test this. This was the simulation. In reality, you found out that the light for the electricity for the light, which is this part, was way too much in this building where you are now, and this has to be fixed now. This building here, this is the ETH hit, this is the building where you're in now. So this amount has to be brought back to this level or even lower by adjusting the technical system in the building, which is a software problem. Okay, coming to the end, simulation and urban design. This seems strange, I would say. This is headlines from the China Daily that came out yesterday, and there is a strong link, for example, for urban design, because people find out with the divorce rates now also in China going up, they have to plan for a different type of lifestyle of people, because the family, many people living in one apartment, or even a couple living together in apartments, doesn't apply anymore. The space needed for the individual is growing up by the fact that more people are getting divorced. So this is having a direct impact on the layout of the cities. And this is one of the parameters that they use for simulation of the new cities. But you can have beautiful examples of simulation of old cities with people. You will see more of this in the City Engine example in Jan Hallard's lecture. You can use simulation, growth of trees, movement of traffic in cities for city planning purposes, or the growth of entire cities based on models that you develop beforehand. Here this is the part of Dübendorf, which is the airport now. Also in this work of your colleagues from the 2009 elective course. It's a very nice course example. So you can use simulation also for these types. Let's come for conclusions. What is simulation? Revisited after 3 lectures on simulation now. It's a method next to theory and experiment in science, and next to theory and design in architecture. It helps to predict form and behavior of complex systems such as architecture and cities. Time is an important factor in simulation. How do you do simulation? It can start with imagination, design and model building. Increasingly, computational methods help to generate desired and realistic future scenarios. And why do you use simulation? It should occur in the early design phases and in the early building management phase to reduce costs and to increase sustainability of architecture that you design and of the cities that you design. And wrapping it up, simulation, I think, is one of the most powerful methods to increase design quality and sustainability both locally and globally in the future. So thank you for your attention and have a wonderful afternoon. Thank you.